Welcome to the Decode. This is Rev 1.15. Somehow we've already made it to 15 episodes. So this is Daniel Stanfill with Aurora Boardworks. Elias, go ahead.
This is Elias Malpavon with Metal Etch Services.
This is Elias Malpavon with Metal Etch. This is Sean Kincaid with K&F Electronics.
And this week we have David. I was going to introduce you. I've never said your last name, so I'm just not going to. And you,
it's just like it's spelled, dude.
What, Kruidhof?
Yeah,
Kruidhof.
There you go.
And
Kruidhof.
Technical Sales Manager at Comet Exelon. Says here you're an electrical engineer. You never told me that, so I don't believe it yet. Also, San Diego chapter office and SYP committee member of the SMTA. We all love the SMTA here. X-ray dude. It's all in caps, so that was as much enthusiasm as I could muster.
You can stop right there. You don't have to keep going on the bullet points.
And I'd say probably the most important bullet point, and just fun facts. We always like to include little fun facts about each person. Is David has met Elias and myself in person. Sean, have you guys met?
No.
All right, great start. So, David, how long do you think you'd say, how long have you been in the X-ray world, and what do you like most about it, if you want to start there?
Yeah, X-ray world. I've been in electronic manufacturing for, almost 13 years. And so I've been around X-ray. I used to sell soldering irons and solder paste as well. So you have to X-ray it to check it out. So definitely, on the periphery of it. But it wasn't until about 6 years ago that I started working directly with X-ray full time. So I love X-ray. Wise old man once told me that don't get into it because you'll never want to leave. And that's because it's really interesting. I'd say electronics is probably one of the least interesting things you can look at with X-ray, but you can X-ray anything. And a lot of industries use it that you wouldn't expect. A lot of industries don't use it yet, but they could. And so it's just a lot of fun to take an engineer's product and put it in an X-ray machine for the first time for them. And they're just like so excited, right? It's like when you were at our lab in San Jose. It's just like, oh, I could hang out here all day.
Yeah, I wanted to.
What did I bring? What can I just stick in
food to get me away from there? Can we talk about what you had scanning at the time, just the technology you were working on at the time?
I'm trying to remember what different things we were doing while you were there. Of course, there were the circuit boards. Beneath had a small board.
Glass. It had been laser drilled.
Yeah.
Drilled
so that was something picked up from a fellow exhibitor at an IMAP symposium. Glass substrates are kind of, I wouldn't say a new thing, but sort of becoming a bit more popular. Just like with silicon substrates, you have to drill holes through them. It's like doing a board PCB fab, but much smaller. So with glass, they're making these really, really thin, incredibly immaculate sheets of glass, and they're drilling holes with lasers in them. It's called TGVs or through glass via, to make those connections between the die down to the interconnects that are going to go on the boards that you guys handle. So it's kind of this
cool.
crazy new thing.
Cool
and at least to me, it's new. So the exhibitor I was talking to, he just was wondering, hey, can I X-ray this? Will this work? I'm like, I don't know. You got a piece I can throw in a machine and see what's going on. So and it worked. We could measure those TGVs, and I forget how wide those ones were, but measuring in microns, right? 50 microns, 20 microns. Just tiny stuff that they're using inside the chips.
It's wild to me that there's like you said, there's multiple uses for an X-ray. I just always think of electronics or bones,
Yeah.
Even just within electronics, there's so many different uses, right? You're using it to validate solder joints on a BGA. You're using it to ensure the authenticity of a component. You're using it to count components, right? It's just, even just within our space, there's so many different uses.
Yeah. Inspecting traces on boards, to make sure you got what you ordered, especially military related things, right? You guys know the PCBA. I think it's 2 A's at the end, right? He's trying to get board fab back in the USA.
We're all 3 members, in fact.
Oh, perfect. Because now we're going to be making chips if this all works out. We can assemble boards here, but hardly anyone actually fabs boards anymore. And so if you order that from overseas, and if they actually know what it's going into, they can add something in there, right? One of those, military boards going to be 20 something layers. Not too hard to slip some extra copper in somewhere that's antenna or whatever, does something that it's not supposed to. So
yeah, I think there's been some contemporary examples of that in the news, right? Without getting too much into it.
Yeah, I don't think I've read anything like specific about it happening, but I know it's something that I've talked to people in that space about. Just wanting to make sure, hey, we actually got what we ordered. We sent this, the files out, and what did we get back? Passing electrical test, it's fine, but what's actually inside of it, I don't know.
All of us kind of have some information of companies that you'd be surprised to learn, like things they've done or, are still doing, so it's just kind of one of those things that not everyone plays by the rules. So you have to do something to help incentivize bringing fabrication of boards, components. Assembly too. Yeah, sure. There's plenty of places you can get assembly here, but there's plenty of places you can get assembly even cheaper elsewhere. It's the same way it is with everything. So you have to be able to give enough value adds besides just the price, right? You have to be able to offer them other value beyond just the cheapest price.
Yeah. And that's why, at least in like Southern California, the vast majority of the EMS providers are doing military, space, medical, although a lot of that's
because it can't go somewhere else.
Yeah, things that can't go for national security reasons, or just incredible reliability, right? You need to have somebody really there watching it happen.
Yeah, I talked to somebody whose products have to last decades without use and be able to count on it to use when you need it. That's definitely high reliability. You really have to learn best practices. You probably can't make something like that without X-ray, I imagine. How could you actually build something to that level of confidence without being able to look at the guts of it, right? There's probably going to be some through-hole components. Is there any way without X-ray to get a true look at a barrel fill? No, right? The only way you're going to know is with an X-ray. So,
you can look at the other side and make sure solder got over there, but I've witnessed people solder one side and then solder the other side. Looks like it's a full barrel.
Yeah.
Not what you're supposed to do.
Both sides.
That's a big no-no. Yeah.
Yeah. Don't do that, but I've witnessed people do it.
I'm joking.
It's like an Oreo with frosting all around the perimeter and nothing in the middle.
Yeah. My quality manager was always yelling at me. I'm like, just add it from the top. And she's like, no, it doesn't work that way.
Don't say that on a live recording, Sean. Your customers listening.
It's okay.
I know. It never stops him.
I'm not worried.
All 10 of them.
Yeah. Come to me and I'll give you the best service you ever seen. Something like that. I don't know. But what's the coolest thing you've ever actually?
Ooh, coolest thing.
Toothbrush.
That was pretty neat. The CT
the Sonicare.
That was pretty cool just to see what goes inside of a Sonicare toothbrush.
There's a lot of components on that board too.
Yeah, and a number of boards, right? I'm sure there's a bunch of flex circuits in there as well. iPhones are always impressive. The amount of stuff they're shoving into the board in your phone is incredible. We had a cadaver leg in our lab. That was weird.
Was it like real?
But the end user wants to X-ray the bone to check on the bone quality for bone grafts or something like that. So it's one of they're going to CT the whole thing, and they'll know what quality the bone is. I don't know, but it's one of those things that I wouldn't never have thought of. I don't live in that world.
What's the largest thing you can X-ray in one of your machines?
Our largest one, we just I think it's kind of a soft release on a full car battery pack. So if you were to take that, the whole, those are the base of the car, right, from tire to tire. So they're, I don't know, a ton, literal ton or so in weight. But wow. People need to, especially in forensic analysis, if something happens, they want to find out why this thing broke, right, or exploded or whatever. So X-ray is used in that world all the time. Yeah, we have some cool ways of looking at those huge battery packs because they're just really big, right? Very, very dense. So we had somebody come to us and say, hey, we're going to need a 1 mega electron volt, which is a lot of power, to X-ray these battery packs. And we're like, you don't need to go that high. We do it at 600 kV, so 600,000 volts instead of a million, right? So a lot less power, but we're able to do it because the way we manage it and scan it can get you 3D results without having to go through the more difficult side.
In terms of X-ray use within the PCBA space, historically, when was the point where it started to become a little bit more widespread, or when was it really introduced? Was it with the advent of bottom terminated components, or was it used before that? Maybe even when through-hole technology was predominant. Tell us a little bit about the history of X-ray in the PCBA space.
I don't think it was very popular with through-hole, and part of that was everything was kind of easy to do. You were using tin lead solder then, so things flowed really easily, really well. Things weren't very small; they weren't very densely packed, so you could really see if you did a good solder joint. Right? You didn't need to look with X-ray. There was nothing on the other side of the board, right? So you'd solder on one side, you'd look on the other side and see if you did okay. But I mean, sure. Tin lead solder was just a million times easier to solder in every single way than lead free is. I don't know if you guys are using tin lead for anything still, but
sometimes,
man, the stories I've heard in the industry from people who were around during that transition, everyone hated it. But yeah, once we got into bottom terminated components, then it's like, well, now what? You can't see it, right? And so when that first started, people used to take their boards over to the doctor or the hospital or the dentist or something to use their X-ray machine because they didn't have one. And then you develop the film or whatever, which is, it's just kind of crazy to me. I mean, Daniel has told me his 2-hour drive to go X-ray things now, but at least they have a good digital system, right? It's a different world. So I think that's definitely what got it going. And as SMT has just almost completely taken over, it's helpful for everything, even just your passes on your board. You can check out the fillets with AOI and make sure they're not cold joints or something. But, if you really want to get an even closer look, you can check for solder splatter underneath it. You can check for voiding in it. Most people don't really care enough, but it's something that you can do if it's one of those things you're making that's going to Mars, right?
Right. If you're trying to drive towards a zero defect process, then you care about all that stuff,
Yeah. Yeah, exactly. And the cost, of course, is much lower than it used to be, or ease of use, I should say, is really a lot lower. They're not cheap machines, although you can get pretty low cost systems out there. Depending
how
on
long, if you've set up somebody with your platform, can you take a employee with zero experience reading scans and within a week or two have them understanding how to tell what they're looking at?
Honestly, it'd probably be like an hour or two.
An hour or two
to be able to put their board in, take a 2D shot, and know what they're looking at. Yeah, as long as they have some knowledge of PCB assembly.
Yeah, sure.
That's what a resistor looks like. That's what a capacitor looks like. Here's your solder. I mean, those kinds of things are not too hard if you already have the background knowledge, right? You know what things to look for. You just want to know what they look like under X-ray, right? So then the next step would be, well, what's a good solder joint look like? A bad one look like? And then you might want to learn some of the more advanced features, like programming the system to do go here, go there, take a picture there, do laminography over there, do analysis here.
What
It's not
about
that
head and
hard.
pillow, which you said was all the rage? That's kind of a harder thing to get to the root
Yeah.
of, isn't it?
Head and pillow has always been one of those things that everyone wants to be able to find. You really don't see it very often. It's kind of a mysterious thing. If you're running a board through a burn-in test or something, it heats up and starts warping, right? A little bit of warpage and that disconnect happens and it suddenly stops working when it's hot.
Yeah, or even coplanarity issues
tests
within the individual component.
Yeah, exactly. And then if you kind of push your thumb down on the BGA and now it's working again, okay, probably have some of that coplanarity or warping or head and pillow type defect, some kind of open. But to see an open in X-ray, you have to look. You have to look at an angle. You have to look ideally on the side. If you get a 3D rendering, you can see it really easily from the side. But you can do it with the 2D angled shot without too much difficulty.
So is the interpretation of the images the X-ray is producing largely done by an operator, or I would imagine at some point in the product offering it starts getting into software interpreting or AI even maybe starting to come into play a little bit. Is that true, or am I wrong?
It depends on what machine you bought, on how knowledgeable your operator is, what you're even looking for. If you're looking for bridges under a BGA, anyone can find that. That's easy.
Sure.
If you want someone to go and look at every BGA that comes off the line for a head and pillow and you're on a manual machine, then you're going to need a little bit more training. Again, probably not really that much. But any AXI, which is inline X-ray machine, they're going to have a tool to help you with that. They should be taking some angled shots, getting some 3D renderings, and having the software do that analysis for you. We don't make those. I've only got to, watch them from the sidelines. So I'm not as well versed with AXI as I am with MXI, but there's a lot of cool stuff out there that's going on. But even MXI systems, the manual X-ray like ours, there's plenty of analysis tools on it. Right? I can take that 2D top-down shot of BGAs, basically draw my region of interest. It's going to find the solder balls. It's going to decide what's solder, what's not. It's going to calculate the number of pixels that are solder balls, the number of pixels that are voids, and do all kinds of analysis for you, like voiding, roundness, size, diameter, make sure they're all kind of similarly shaped. And that's not just us. I mean, that's pretty common to the industry. The next step, which is pretty neat stuff, and this is where AI starts getting more involved, is we're doing this on the chip level for advanced packaging of semiconductors. They're actually taking that silicon or whatever interposer, putting multiple dies on it. They're stacking memory dies on top of each other up to 8, 12, or 16 high. And again, this is like crazy that people have figured this out to me, because the memory stacks that are like 16 high, the interconnects, the TSVs, through silicon vias, are like a micron or two wide. and there's 16 of them all lined up. It's like, I don't know how you do that. I mean, right, in the PCBA world, we're like, oh man, I got about a micro BGA down. That's really hard.
Oh man, I only have a half a millimeter in between each one.
Yeah, exactly. So it's crazy that those things are happening. But in that stack, the last kind of portion where you're putting that all onto a substrate, which can be, it's just typically like an FR4 material, but not always. But there's a C4 bumps that are about 50 microns, 50, 60, maybe 40 microns wide. And so we have a tool that can do laminography on that. So you're in 3D rendering. And an AI, once you tell it what slice, or what slice you're looking at, it will do all that analysis for you. It'll look for head and pillow. It'll find it. It'll look for tilting, coplanarity issues, all this kind of stuff that can just give you answers, right? Because at that point, you don't even want to look at the picture. You don't really care, right? You just want to know, is my stack of chips good or bad? Can I go sell it for $5,000 or not? So these things are expensive. All the generative AI chips, it's pretty crazy.
I feel like I know you're going to know your answer right now, but I always like to talk about the future of where you see your industry going. And it's kind of wild to see the progression. Like we started with 2D X-ray, right? Then we went to 3D X-ray, and then we have now the AXI that can slice individual layers. What could possibly be next?
I mean, the main thing that everyone's pushing for is faster and smaller, finer details. Right? Like I said, they're stacking those memory die on top of each other with 1 or 2 microns wide. Right? The industry is chasing down Moore's law, right? And so we're just trying to figure out how can we keep packing in processing power? How can we get the heat out? It's a whole different problem. But as you pack things in and you start stacking them up, then you have the bottom terminating component issue, right? I can no longer see it with a microscope. And of course, a lot of these things you can't see with a microscope. You need a scanning electron microscope. But again, that's just on the
You
surface.
don't have a 30,000x magnification microscope at your facility?
Not in my house. An eye loop. 30,000.
It's a real good one.
So that's really what it comes down to, is that we need to be able to see smaller and smaller and smaller and smaller stuff. I mean, they're placing layers down. I mean, I've seen different companies advertising this like an atom thick. Like how do you do that? How do you know you put an atom down? Beats me. But that's just kind of the scale that we're talking about to keep chips.
Can you get
path.
those people on the podcast?
Maybe.
What would we talk about? We wouldn't understand anything they said.
Yeah, right.
Just pretend we understand what you're talking about and tell us. That's crazy. Man.
Yeah, it's really neat what's happening on the chip level. I mean, when I first started learning about it, I learned about like flip chip, right, which is basically a BGA inside of a BGA. I'm just like, everyone hates BGAs. Why did you decide to do that inside the component on a smaller level? Why did you know? It's a bad idea. So now they're doing that with smaller and smaller pieces and stacking them on top of each other. So it's pretty amazing what's happening in those fabs.
So is it just the magnification that's really helping out with it, or how else could you
primarily
achieve that?
So X-ray, to get an X-ray image, there's like a bunch of different levers you can adjust and play with. So to get you a good image clarity, you need to throw a lot of X-rays or take a longer exposure, kind of like a normal camera, right? If it's dark out, you can do a long exposure. You'll get more light to the film or to the sensor and get a good picture. Similar principle, right? But the problem in the X-ray world is the more X-rays you try to generate, your focal spot, which is where you're creating those X-rays, it gets bigger. And so, on a lower end X-ray machine, you're going to have, for the electronics world, you're going to have a 10 micron or 5 micron focal spot size. Well, if you have a 5 micron wide focal spot, you want to look at something that's 1 micron wide, it's not going to work. I don't know if you want me to dive into all that, but basically the smaller the focal spot, the better. So, these latest and greatest ones are having, 200, 500 nanometer focal spots. They're tiny. And so we're just trying to get down to these smaller and smaller details. And so the X-ray source has to match that. And then your detector on the other end has to be sensitive enough to see it all. But the more power you throw through it, the harder it is to control that electron beam or the lightning bolt, basically, that you're creating to generate X-rays.
All right, David, if you could, can you just give us kind of a brief layman's explanation of how X-ray technology works? Something that's, kind of Sean speed that anybody could understand?
Yeah, and Sean, let me know if I'm going too fast.
But, you got it, buddy.
So to generate X-rays, what we typically will do, for at least for this industry, is you have your a filament or some sort of emitter that you're just driving a lot of current through, and typically the filament looks a lot like a light bulb. Right? It's just very thin. It's tungsten wire. You run a lot of current through there, so you have a lot of heat. You have kind of excited electrons there. And then you have a voltage difference over to the other side, and so you're exciting these electrons, and eventually they start flying off towards that voltage difference. Right, they get attracted to the other side, and you have to control those electrons so that they hit their target. And that's where the focal spot size comes in that I was talking about earlier. You're basically trying to get that lightning bolt to hit, 1 micron diameter circle or smaller. And then when those electrons hit the target, they excite an electron in the atom there. And so if you remember from your chemistry/physics, the electron moves to an outer layer. When it comes back in and settles back into neutral, it launches an X-ray photon. And so you're doing this, a million times a second to create enough X-rays. And then they come out in this big cone. So from that little focal spot into a cone that flies out. And so then it's going to pass through your sample, and there'll be a detector on the other side, which has a scintillator material. And there's different kinds of scintillators. Basically, it's like night vision, right? So if you're wearing night vision goggles, it has a scintillator, and that's why it's green, or at least it used to be green before they got digitized. And so when a small piece of light hits that, it magnifies it. It shines out more light, so then your eyes can see that. So that's how night vision works. But with X-rays, you have invisible light hitting it and then creating a visible light. And so within the detector and all that detector technology, you have that different kinds of scintillator. You have different thicknesses that have pros and cons. And then you have a photodiode layer that looks at that visible light and turns that into something that you and I would then be able to see. So part of the cool thing of that is those photodiodes can see, they usually have 16-bit depth, which means there's over 50,000 shades of gray that they can see the difference on, which is just a ton of information in each and every pixel on there. And our monitors can only show, maybe 256 shades of gray, and our eyes can detect even less than that. So there's just a ton of information in there.
I was wondering that if the monitor is actually the weakest link in the resolution.
Sounds like our eyes are.
Our eyes are. That's true. That's not even speaking of resolution yet. That's just a matter of the different data, the different energy level that the X-rays are at when they hit it. And so on any X-ray machine, you're going to have the ability to adjust your contrast, right? So you have your 50,000 shades of gray, and you can say, well, let's just use my 256 on this chunk of it because that's where my information's at. Or when you get into more advanced image processing, which again, most everyone has, we call it HDR, high dynamic range, or EHDR filters that will take all that information, and it will present it in a way that isn't exactly its true gray value, but it'll allow you to see the differences in the lighter area and your differences in the darker area. Whereas straight contrast is just going to allow you to see one area at a time, or see the differences in one area at a time. What energy level that X-ray photon has when it gets there, that is determined by a number of factors, but primarily it's the material it's going through, right? So if you have a board, for example, your solder is metal, it's a denser material, it's going to slow down or absorb more of those X-ray photons, and so you're going to have a darker image in that area on the detector. Your copper is fairly dense, but the traces in the board are pretty thin, so those are going to show up more than the organic substrates or the F4 material that's in the board. So you have a pretty good contrast between your fiberglass and the copper, so you can see those traces pretty well. But then solder joints are just relatively very dense, so those pop and shine really easily.
What about aluminum boards? Are those difficult to X-ray?
Aluminum is pretty light, actually. So if when you get into some of the space stuff that have 20 layers or a thick bottom, just like solid copper layer that's like a millimeter or two thick for
like
grounding
Iconel or something.
Yeah, those can be a bit more of an issue, but it really shouldn't be a problem. It just means that you're probably going to have to use a little more power, which means that your lighter materials that are behind that heavy material is going to be harder to see. So if you do have that thick layer of copper across the whole thing, it's going to act as a filter. And so you might not be able to pick up the subtle differences in lighter materials. But again, if you have, well, for those, you probably have tin lead solder on them. And lead is a great X-ray opaque material. We use it for shielding in the cabinet. So it stops X-rays pretty well. So you can see that pretty easily.
Sure. I'm thinking of the lead vest that they put on you when you go to the dentist,
Yeah. Yeah. Same idea. So yeah, that's why all X-ray cabinets are really heavy, because we all use lead to line them. I think one company was trying to use concrete for a little while, because that material is used as well in like big bunkers for like large, the NDT world to stop X-rays.
Sure.
But it doesn't work very well in a cabinet. You move it around and it's kind of brittle. But yeah, as far as aluminum and copper, gold is very radiopaque. So you were talking earlier about looking inside components to make sure that like the lead frame, the bond wires, all those things are consistent with what you're expecting. The gold would show up under X-ray really, really well. Copper shows up pretty well. But then people started using aluminum alloy bond wires, and you basically can't see the aluminum in there. It's a lot harder to put it that way. A lot harder.
We were looking at a job that had some gold-plated tungsten wire.
Wow.
And that stuff's expensive.
Yeah, that stuff will shine really well under X-ray.
I imagine so.
But they use that in like surgery, right? When they're going up your different veins to do heart surgery or something, they'll have a little radiopaque ring of gold or tungsten or something like that. So they're operating under a live X-ray scan, so they can see where they're going and what they're touching and where the devices actually are in your body. Again, X-rays are everywhere. We just don't think about it.
Talk to us a little bit about your involvement in the SMTA. Are you still fairly active there? Do you just attend events? Are you still on a committee? Did you jump ship to the OC chapter? Talk to us.
Do you just help Sonia at booths, or what's your actual role?
Yeah, so I was an officer in San Diego for, I don't remember how many years, 5 years or something. And then passed the torch on to someone else. And now that I moved up to Orange County, I've been to the last two events that we've had since I moved in August. But yeah, I plan to be active. I've spoken at various meetings, chapter meetings here and there. So I do like to participate. I think it's a good organization. I think we have a lot of work to do to get the next generation of people in. It's nice to see that there were 40 people under the age of 40 that went to SMTAI.
They said it was a really prestigious group. It does make you wonder, was there 43 submissions, and they...
Well, aren't you over 40 now? So, maybe less than 40 submissions.
I'm not. Elias is, though, so it's good to point that out. I'm definitely still under 40, a couple of years. Elias is definitely 40, only gets older.
Yeah, a whopping 5 months.
Yeah, when I was an officer in San Diego and the SYP was starting, they asked us officers, hey, make a list, go through your member list and find everyone who's under 40. And it was me. And now I'm over 40, so that doesn't help any. But just like, wow, this is kind of a wake up moment, right? We need to. It's a good thing we're starting this SYP thing. We need to get it going.
I think the wake up moment for me was the fact that we were getting treated like children in the industry. Like we're so young in the industry for, like even though we're all right around 40, it's like, well, you still have your whole lives ahead of you.
It's kind of nice.
When I started in the industry and I went to my first trade show, I was a little taken aback. Like, is this really where I want to go? But on the other hand, it's like, well, there's going to be lots of opportunity here in 10, 15 years. But yeah, everyone was pretty old, fully grayed, all that good stuff.
That's what I told my little brother. I said, if you entered the industry right now, you'd be a seasoned vet by the time you hit 40.
Yeah. And the great thing, and SMTA has a lot to do with this, is most of these people are happy to pass on their knowledge. Right?
Yeah.
I mean,
totally.
You can.
That's been the coolest part to me, that community, that network of people that are excited, not just willing, but excited to find somebody who wants that knowledge. So they're eager to participate and pass that torch. And I think that part's been a lot of fun for all of us, getting to be involved with people who have such a lineage in the industry, such a history of achievements and accomplishments and pedigree. It's fun getting to work with stuff and be considered on their level. Like, it's, I know, exciting for me. I'm sure it's exciting for at least one of the other two.
It's almost for me personally, it's almost, I don't know if starstruck is the right word to say, but when you talk to these experts, and they give you the time of the day just to even respond, it's, I don't know. It's not like a celebrity or whatever, but it's like someone you look up to, and it's just, I don't know. For me, the thing is like, I just found out last week that the Michigan and Ohio SMTA chapter is going to put on an event November 20th, and it's about like inventory storage or something like that. I don't really have too much details on it, but there's how many people know about that event even existing, and the other day, I think it was like North Carolina or South Carolina chapter put on a event about solder paste printing. And I attended that. It was online. It was kind of nice, but is the word even reaching the people? That's kind of what's wild to me. It's like I have to like search for that information. I have to scroll through my feed a whole bunch of times before I even stumbled across that.
Really does need maybe a podcast or something to talk about that.
If they give me another award, I mean, we'll just keep talking about it. Like that's all it takes for me. Like you.
Monetary.
Give me a little bit of flattery, and I'll give you all the promotion you need.
You got your champion badge.
It feels like there's a bit of a groundswell movement right now, and I think kind of the folks that have been around and involved in SMTA for a long time are really, making an effort to embrace, quote unquote, the younger folks within the space and kind of hand the baton off. So I feel that way, and I think we've all kind of experienced that. Just kind of getting back to what we were talking to, these folks that we would all consider icons in the industry, treating us as peers, like that kind of says a lot, right? So I think we're headed in the right direction.
That knowledge sharing is a big, big deal. I mean, as I've been with SMTA and trying to get new members, especially younger members, where there's the big success is at the company where there's somebody older who's involved and just kind of takes these younger ones under their wing and says, hey, you want to learn stuff? Here, we're a corporate member of SMTA. Get your login, go online, read the white papers, go through some of the training. We're going to have a chapter meeting. You can go meet some people who all would love to teach you whatever questions you have. But to just come into the industry and be aware that it's there, it's not going to happen, right? So it really takes kind of word of mouth to keep spreading. And so I've seen it happen at large companies, at small companies, but definitely not on the scale that I think our industry really needs, because we need to pass this knowledge down to the next generation. Just kind of a requirement for it to continue and keep going on. Right? I mean, this whole CHIP Act thing, we're trying to bring back chip manufacturing to the U.S. Well, we haven't really done that at scale in a long time, but guess what? There are people who did it. They had to pivot into other things, but there are people who have some of that knowledge, and we need to be able to share it and teach new people how to do it.
Well, look at what SpaceX is doing. It's not like they started out with all that knowledge. They've got there from iterating through failures and successes. But I mean, you've got to be willing to learn. I mean, you can't start out from the position of already knowing. You have to start out where you are and learn and get better. And if we're always, if you don't see the results from exercising until 6 months after you start or whatever, you're still never going to get there 6 months later if you don't start now. Like you have to start somewhere. So, I mean, we just got to, the industry as a whole just has to we can't let it out of our sights. You got to keep pounding the message, really. Just the PCBA kind of message, just get that out as much as you can. And I think all the other being involved in the SMTA and other organizations, I just think all that kind of stuff builds a stronger industry through network connections and shared collaborations and shared knowledge. The more we can do that and facilitate that, be a bridge for that, I think we all come out ahead, right?
Yeah, and I just posted about the expo we had for SMTA here in Orange County. And the panel was talking
thanks
about...
for the invite, bro.
Speaking of not enough publication, right?
Yeah. That venue was amazing, too.
It was, cool. Yeah. It was really cool.
With the cars and everything?
Oh, yeah. Really neat. So they were talking about ultra high density interconnect. And basically just at the board level, you're going to have to make things that are smaller. Tighter tolerances, smaller and smaller and smaller. And they're already doing this. On the latest iPhone, they're doing this. But we don't really do it at volume in the U.S. And we're going to have to learn. Everyone's going to be requiring it at some point. It's like the change from through-hole to SMT, or the change from tin lead to lead free.
For that miniaturization, it's everything, though. Your screen printer has to be capable of it. Your stencil design and all that has to be on point. Your pick and place has to be capable of it. Your reflow, understanding and profile has to be perfect. Your inspection capabilities has to be, able to see those parts. And then how do you rework it? You can't, right? So at that point, I mean, surely you can't rework an 008-004, right? What are you going to do with that?
There are some very skilled people, but generally speaking, you have to decide if it's worth it, right? Or in some applications, they just don't let you rework things. But either way, we're just, the process has to be dialed in perfectly. I mean, some of those things you post, Daniel, on showing the printed solder before it reflows, it's a little bit off the pad. Well, that's fine if it's 0.05 or something, but not okay if it's a smaller one, right?
Yeah, the amount of overhang makes no difference on a component that size. If that's an 0201, you might be bridging together with that kind of overhang. So,
if it's an 0201 metric, you might be off the pad completely.
Yeah, that's right.
Oh, yeah, and they're getting smaller, too.
Yeah, I mean, they're talking about 0.3 millimeter pitch BGAs. Like, oh, that's fun. It's the pitch, not the ball size.
Ouch.
And then from the board fab size, they talked a lot about the fab of them a lot. Doing less than 50 micron, wide traces within a board. I mean, that doesn't sound like fun.
How often do you get to travel for work?
I travel quite a bit. Seems to be kind of seasonal, but probably about every other week, typically on a plane. Yeah, I get to visit customers, which is a lot of fun to see what different people are doing. I mean, you mentioned SpaceX earlier. That was a great place to visit. It was just like, sci-fi, where people are just running around making a bunch of rockets. And you're like, what's happening? We're doing this for real? Like, this is how it's done. You got to see the Raptor engine outside on the street. Like, it's so much bigger. than on a tiny screen, right?
Oh, sure.
I can't imagine standing next to the Starship. I mean, that thing, then that's
Stories tall, right?
yeah.
I mean,
I think it's like
massive.
60 stories tall or something.
Yeah.
So seeing what people are doing both in the space sector and the medical device area, I mean, all these different things that people are doing is just, it's cool. It's a lot of fun. Never used to, I guess I get kind of used to being on a plane, but it's still not fun. Don't like airports yet.
Go ahead, Sean. You got something. I see it. You were right about the spring.
It's a 2-hour wait for me. I can't stand that. Where you got to get there 2 hours early.
The airport?
Yeah, it just drives me nuts.
Actually, the trip out to PCB West to come hang out there, David, I think I told you that day started. My flight was leaving at 5:32 a.m. and I got to the check-in counter and everything to get my boarding pass 45 minutes before the plane departed. And the lady was telling me as she was printing the pass that if I was 1 minute later, it wouldn't have even let the system print the boarding pass for me. I don't know if that's true or not, but I definitely did not give myself 2 hours. And it's actually quite a bit more comfortable if you give yourself the time and don't have to worry than it is rushing to your gate, especially in a bigger airport. You don't know where it's at. Like, oh, man.
Yeah.
I'd rather have the time to kill than be stressed about whether I'm going to make it or not. David, before we go, we want to make sure we give you the chance to talk about Comet's offerings, what you do there. Go ahead, plug anything you want to. We really appreciate your time joining us. So tell us what you do at Comet and what Comet does better than other people.
Yeah, so Comet, we have two divisions of our company are involved in X-ray. So we make all of our own X-ray tubes. We actually make X-rays for all kinds of industries. So when you go through the airport, the security machines probably have a Comet X-ray tube inside of them. But Comet Exelon, we make systems, right? So we make the cabinet systems where you put your product inside and X-ray it. So our focus is really on the MXI, manual X-ray systems. We have some automation when it's inside, but our focus is really on high precision, high resolution, get you the best, most detailed image you possibly can. So some of our larger machines, we have some really cool trajectories to help you get really like sub-micron voxel size for large samples inside in a full 3D CT result. A lot of really cool stuff that we can do, but we do have a lab in San Jose, California. So if you want to just stop on by or bring something to X-ray, we're happy to host you and see if you can see what you want to see.
I can attest to that. It's a very cool lab, very cool facility. It's a lot of fun to visit that. And hopefully, I don't know, we have to share any details yet or anything, but hopefully I'm sending you something that you'll be able to scan and we can show fun images from your platform on LinkedIn, because that's kind of fun to do. So
yeah,
just tell the people to stay tuned for that. But
yeah, I'm looking forward to it.
All right.
I always bring my trash to the lab to X-ray.
Yeah, why not? Right? Got to be a perk. Got to have some extra perks of the job, right?
Yeah.
I've fixed a few things soldering at work. Like brought something that wasn't working, soldered the connection back together. Hey, here we go. Fixed it, but
that's right. Perks of the job, right? We know how
that's right.
Work. My kids broke my TV, and I was like, "I'm going to fix this." And I looked it up, and everyone's like, "It's not worth it." To buy a spare screen is more than just buy a brand new TV. It's like
unbelievable.
Oh well.
I believe that for sure.
Some things aren't quite worth repairing, but a lot of times.
Right. But TVs they are essentially disposable at this point. Just get a new one. They're $70 for a 120-inch 4K TV now. So thank you for joining us. It's been a lot of fun. Hopefully everyone enjoyed it. I learned more about X-ray. Hopefully other people did too. And we will be back next time for Rev 1.16. Until then, thank you.
Thank you, guys. Had a good time.